we find is that looking at the invariant quaternion algebra, it's given by a collection of primes. You just look at those primes, Snap will list them, and you see that in all but 3 cases, the primes are not, the set of primes you find is not equal to itself after complex conjugation. So looking at A of m in all but 3 cases, A of m is not equal to A of m conjugated, so m has no cover, which admits an orientation reversing homeomorphism. And in the remaining cases, A of m, where A of m is actually equal to A of m conjugate, a priori we don't know. But it happens that these 3 cases are arithmetic. And I'll talk about, well, I was hoping to talk about arithmetic later today, but M does have such covers. And this is a consequence of it being arithmetic. Okay. So we get an exact answer to this question of orientation reversing things. So maybe I have 10 minutes left. So maybe I'll simply, since I've mentioned arithmetic, I think I'll finish simply by telling you what arithmetic manifolds are. I'd hoped to have time to do some computations too, just to show you how easy computations in algebraic number theory really are. They're nothing to be frightened of, but I don't think I'll have time for that. So I want to describe to you what it means to be arithmetic. So you've seen this before. In some generality, but now I'd like to specify this to hyperbolic 3 manifolds. Okay. So just to remind you, an arithmetic group is a group which is basically the set of integer points in some sort of an algebraic group defined over some field. And this algebraic group, when you look at its C points or its R points, will be a Lie group. So your arithmetic group then becomes a lattice in some sort of a Lie group. And in the particular case of PSL2C, there are various descriptions of PSL2C as an algebraic field, giving you various different ways of defining arithmetic groups, but it's a result of Borel that there's one nice uniform way of describing all arithmetic subgroups of PSL2C. And this is Borel's construction. So you start with K is going to be a number field with exactly one complex place. A is going to be a quaternion algebra over K, which is ramified at every real place. So in other words, when you take one of the real embeddings of K and tensor with the real numbers, you get the Hamiltonian quaternions always. And O contained in A is going to be an order. So let me remind you, And Professor Choi described what this means, but very briefly what this is it's a subring containing the ring of integers of the number field and of rank 4 over it. It kind of plays the role of ring of integers. The problem with a quaternion algebra, you can still define what an integer is just the same way you do anywhere else. It's something that satisfies a polynomial, a monic polynomial with integer coefficients. Unfortunately, the set of integers in a quaternion algebra is not a ring. And so what you do is you look for subrings of this set of integers. It's not unique, but it is unique up to commensurability. So just picking one of them is going to give you an answer that is well defined up to commensurability. And as I've been saying, we're happy to change our things up to commensurability. So we pick such an order, and now then we look in this order. O1 is going to be the set of alpha in O such that the norm of alpha is equal to 1. Okay. And I guess we don't, I forgot, did Professor Choi define the norm of something in a quaternion algebra? I see blank faces. I think the answer must be no. Okay, let me briefly tell you what the norm is. So if we've got a quaternion algebra, it's generated over K. It's 4-dimensional over K. So it's generated by 4 elements as a vector space. I'll always take one of the 4 elements. I'll take 2 that are called I and J, and then the 4th element can always be called IJ. And you can always choose your I and J such that I times J is minus J times I. That's fairly easy to see. And then you'll have I squared as some element of the underlying ring. J squared is some element of the underlying ring. And these are basically the relations you need to describe a quaternion algebra. And this quaternion algebra is sometimes abbreviated as by this notation, the so-called Hilbert symbol. And of course, by changing these generators, you can change the alpha and beta a lot. So the alpha and beta are not determined, but it's rather easy from this description to then work out the things we want to know, like ramification and so on. So any quaternion, any x in A, can be written as x is equal to A0 plus A1i plus A2j plus A3 times ij. Okay. And the norm of x, just like in the complex numbers, is going to be x times x conjugate, where x conjugate is just changing the sign of all of the kind of imaginary part, as it were. So if you work this out, this is A0 squared plus alpha A1 squared plus beta A2 squared minus alpha times beta times A3 squared. So that's the definition of norm. And it's a nice multiplicative thing, so when you take things of norm 1, they're automatically invertible. And so O1 is these things of norm 1. And in fact, the norm, when you embed this into matrices, becomes just the determinant. So O1, if we take our complex embedding, we have our complex embedding K to C induces induces A to A tensor C, which we know as M2 of C, and therefore O1 goes to a subgroup gamma in M2 of C, but norm 1 is the same as determinant 1, so this is in SL2 of C. And this let me call it gamma bar, because it's in SL2 of C, and then I'll take P of O1 in the which sits in the projective special linear group 2C. And this is going to be R gamma. Okay. So by this construction, taking an order and then taking the elements of norm 1, we get a subgroup of PSL2C, which, because orders are well defined up to commensurability, you can check that that implies that this is well defined up to commensurability. And this is what's called an arithmetic group. Borel's theorem is that every arithmetic group is obtained by this construction. Anything that is commensurable with an arithmetic group is also called arithmetic. So this is the construction of arithmetic groups. And notice that in particular, what we're saying is that for arithmetic groups, the quaternion algebra determines the group up to commensurability. So that's why the fact that these three elements, over looking at these 37 elements in the 37 manifolds in the closed sensors, the three for which A was equal to A bar, because they were arithmetic, A being equal to A bar, told us that in fact up to commensurability the manifold is equal to its reversed orientation. So let me finish maybe just to, let's see, I started at 5 of, so I think I have 5 minutes. Which gives me time for one example. I'd like to at least say. Show the sort of calculations that can be done. And these are calculations. Snap does these calculations for one, but for simple examples, they're really things that one can do by hand. And oh, actually, maybe let me say something different and maybe leave the example till later. Because having defined arithmetic hyperbolic manifolds, it's worth saying something about them. And it's kind of miraculous. If you look at these 37 that I wrote down here, almost all of them are arithmetic. And if you look at low volume hyperbolic manifolds, in fact, recently the manifolds of smallest volume, the first 9 or 10, I think, I've forgotten how many, were finally classified. It had long been conjectured what they were, but finally work of Meyerhoff, Milley, and Gabay, I think it was, is that right? Worked out exactly what the smallest hyperbolic manifolds are, and I think all but one of those turn out to be arithmetic. And this is pretty miraculous, because arithmetic manifolds are rare. They're very rare. If you look at knot complements, for example, it's a theorem of Alan Reed in the early 90s that there's only one knot complement which is arithmetic. Among the infinitely many knot complements, only the figure 8 knot complement is arithmetic. It's a theorem of, so among knot complements, only the figure 8 knot complement. I should try to draw this, but I'm sure to make a mess of it. Some people can do this without thinking, but I can't. I should get someone else to do it for me. Do I have to do another crossing here? I think so. Is that right? Good, thank you. There's the figure 8 knot. So Craig Hodgson already drew it, so maybe I didn't need to. But anyway, just wanted to show I could. This is the only one which is arithmetic. And Borel showed that if you bound volume, so if you take any finite bound on volume, there are only finitely many arithmetic manifolds below this volume. Well, on the other hand, there are infinitely many hyperbolic manifolds, in fact, multiple infinities of hyperbolic manifolds, as soon as you get to any volume where you have manifolds with multiple cusps. Anytime you see a cusp manifold, there are infinitely many hyperbolic manifolds obtained by Dane's surgery on that particular one, and their volumes are smaller. So arithmetic manifolds are extremely rare, and it's somewhat mysterious that they arise so often in nature among the. So I should really stop there, and I'll continue tomorrow. Thank you.